Yes. Go
Okay.
ahead.
Hi everyone. My name is Uday and today I'll be talking about our work titled NeuroCNN, a neural operator based model for physiological time series, which has been accepted at ICML this year. So, the motivation behind this work is that physiological signals such as EEG, ECG, PPG, etc., are continuous in nature. So, when we record these signals, in order to save these signals, we need to discretize them. So for that, we use an A to D converter, which basically samples some values from these signals at a at a regular time interval, which is TS in this case. So the sampling frequency becomes Fs, which is equal to 1 by Ts. And after this sampling, the output is a discrete signal which looks something like this, which we can save and process in our computers. Now, when we train AI models on these types of signals, we generally take a large data set which has a number of these samples, and we generally these data sets have these signals at a certain sampling rate, at a single sampling rate. For example, if you take an EEG data set, the sampling rate of the data can be 200 hertz. So we take any model, say transformer, CNN, or anything, and we train that model on this data. So our model, after training, becomes tied to this sampling rate. Now, let's say we want to use this trained model for inference. Now, during inference, the data can come from multiple places. For example, a clinic has an EEG device which samples the data at 100 hertz. Another hospital has another device which is more sophisticated, and that device samples at 500 hertz. Now, when we want to use our model on this data, because our model is tied to a particular sampling rate, what we have to do is we have to resample the data to that sampling rate. Now, when we resample this data, this can introduce a train test distribution shift due to resampling, and which can reduce the accuracy of the models. So, we want models that can handle variable sampling rates and treat the signal as a continuous time signal instead of a set of samples. So, a solution to this problem is neural operators, which we discussed a few weeks back. So, neural operators are basically models that learn a function to function mapping. What that means is that they treat the input as a function instead of a set of samples. So, they can be trained on one particular sampling frequency, and they can be used directly out of the box on any other sampling frequency without resampling the data or fine tuning the model. Now, these models learn function to function mapping. So the input is a function, which can be, say, a time series, any EEG data, but the output is also a function, which also has to be some sort of time series or any other function. These model now, if we are talking about physiological time series, a lot of our problems are related to classification. For example, sleep staging or ECG rhythm classification, etc. Now, in these problems, the output is not a function, it is a set of labels. So, neural operators are not designed to learn a function to label mapping. So, we need models that can learn function to label mapping, which treat the input as a function and can handle any sampling rate, but the output is a set of labels. So, this is where our contribution comes in. So, the core idea of the model that we have proposed is again the input is treated as a function, a continuous time signal. Then there is an operator model that learns a function to label mapping, and the output is n number of classes. So now let's come to the model and see how we are doing this. So this is the main architecture of the NeuroCNN model. So first of all, in the model, we have a set of convolutional layers. Now in a convolutional layer, we have kernels. Now in regular CNN layers, these kernels are basically a set of samples. So the kernel length is a hyperparameter that we set. We can set the kernel length as 3 or 5 or whatever. But the problem with using a set of samples as a kernel is that when we train these CNN layers, those kernels get tied to the input sampling frequency. So instead of defining the kernels as a set of samples, we are defining the kernels as functions. Now, the advantage of that is that if the kernel is a function, let's say this is a learned kernel, you can sample this kernel at any sampling frequency. So once you have a learned kernel, it can handle any input sampling frequency because it can be sampled at any sampling frequency because it is a continuous signal. Now, to parameterize kernels as continuous functions, we are using cubic spline. So let's see how it works. So we call these convolutional layers spline con 1D. These are 1D convolutional layers. Now, first of all, what is spline? So in spline, what happens is you have a number of control points. And what cubic spline does is it connects these control points in a smooth fashion. So, for example, like this. Now, in this case, you have 5 control points, and when you connect these control points, you get this continuous time signal, which you can sample at any sampling frequency. So this is what we are using to parameterize our kernels. So now in our kernel, there are 2 hyperparameters. Instead of defining the length of the kernel as a number of samples, now the length is a physical duration, which can be say 0.5 seconds or 0.25 seconds. The other hyperparameter is the number of control points in the kernel. So once you have a set of control points, you basically interpolate the signal using cubic spline. And this is a continuous kernel, which you can then sample at any sampling frequency. So it's the underlying kernel is the same, but as you can see, the sampling frequency can change. So the advantage is that, say, let's say you are training the training data is at 100 hertz. So you can train the shape of this kernel using signals which are at 100 hertz. But if your inference data is at 256 hertz, you can sample the same kernel at 256 hertz. So it works out of the box. You don't have to resample the signal or retrain the model. So this is how we are handling variable sampling rates at input. So now these convolutional layers basically act as a neural operator. So if the input shape is B by C by N, where B is the batch size, C is the number of channels of the input data, and N is the length of the signal in samples. the output of these convolutional layers is also going to be B by C by N. Now, the challenge with this is that N depends on the sampling frequency. N is the signal length in samples, which is equal to sampling frequency multiplied by signal length in seconds. Now let's say kernel is of, your signal is of 30 seconds. And if you sample this signal at 100 hertz, you'll get 3000 samples. But if you sample this at 200 hertz, you'll get 6000 samples. So the input length of the signal can change even though the underlying signal is the same. And because the input length can change, these extracted features also have a length of n. So the feature length can also change. Now the challenge is that if you are doing some sort of classification task, at the end you need a classification head which basically maps to the number of classes. Now, for a classification head, we mainly use a linear layer, and these layers accept a fixed dimensional feature set. So this n cannot change once you train a linear layer. So how do we convert this variable n into a fixed dimensional feature set? For that, we are using Fourier basis projection pooling. So let's see what this is doing. So the input to this Fourier basis pooling is B by C by N where N can change. So the input signal is this, I hope this is visible, ZB of T, which is a single signal. Now what we are basically doing is we are projecting this signal onto multiple sinusoids of different frequencies. These are Fourier bases basically, which are represented as phi m. So this is the main formula for that. So we are basically multiplying. So let's say if this phi m of t is this sinusoid. So we are multiplying this sinusoid with our signal and we are integrating it. So this gives us a single value. And what that basically represents is how much component of this sinusoidal frequency is present in this signal. And we do this for multiple sinusoidal frequencies. And so these are the bases, the Fourier bases that we have considered. So the first is 1, which is basically the DC shift. And then phi 2k minus 1 is the sine component, and phi 2k is the cosine component. And so in this case, a hyperparameter is the number of sinusoids that you want to use. And you choose this number, which is represented as m, based on what is the maximum frequency that you want in these sinusoids. And that totally depends on the application. For example, if you are dealing with say an EEG task where you want to focus on frequencies from 0 to 10 hertz, you'll choose M so that F max, which is given, which is approximately equal to M minus 1 divided by 2t, where t is the length of the signals. So F max is approximately equal to 10 hertz. So that is how you can choose the number of sinusoids in this pooling. Now, in our implementation, what we did was we first segmented the signal into smaller segments, and then we used this Fourier basis pooling on each of these segments. So for each segment, we get ms coefficients, and then we basically concatenate them. So the final feature vector will look like ms times n segment. So this you'll get after concatenating, and by c, which is the input number of channels. Now, an advantage to do this is if your signal length is large and you want f max to be high, you need a lot of sinusoidal components. And if so the frequencies will be very close to each other. If you don't need frequencies which are that close to each other and you want a higher f max with a lower number of these sinusoidal bases, then if you reduce this t, then with a lower m, you can achieve higher f max. So in our experiments, t was 30 seconds, which is quite large. So that's why we segmented it into 5-second segments, and then we concatenated all the ms coefficients. So now the output of this layer depends on how many coefficients you have. So if you have a total of m coefficients, sinusoidal basis functions, then your output will uh, become b by c by m. So n will get transformed into m, where m is a hyperparameter which is fixed for all sampling frequencies. So Fourier basis pooling basically converts this variable dimensional feature set into a fixed dimensional feature set. So once you have this fixed dimensional feature set after this pooling, you can do anything with with it. So what we are doing is we have used a multi-head attention, which is a transformer layer, to mix these features, and then we are using attention pooling to reduce the dimensionality. And finally, we have a classification head, which outputs all the logits. So this is how our model works. So first, again, to recap, first of all, we have continuous convolutional layers where the kernels are parameterized using cubic splines, which can take any sampling rate as input. These layers give features which are variable dimensional, where n can change depending on the sampling frequency. And to get a fixed dimensional feature set, we are using Fourier basis projection pooling, which converts this variable n into a fixed m. And then we have transformer, then pooling, then classification head. So this is the overall architecture of the model. Now, in our experiments, we used 4 data sets. These 2 are extracted from the same data set, which is the sleep EDF dataset. So it has both EEG and EOG modalities. Then we have ISRUC and HMC. So these 3 datasets are sleep staging datasets, which are 5 class classification problems. And we also used an ECG dataset, which is a rhythm classification problem, which is a 4 class classification problems. Now, in our experiments, to to test the robustness of all the models of our model and all the baselines to changes in sampling frequencies, what we did was we trained all the models at the native sampling frequency of all the data sets. And then only in the test set, we resampled the signals in the test set to multiple sampling frequencies. Now, we compared our model against neural operator based baselines as well as traditional models. So, for conventional baselines, which require a fixed input sampling frequencies, as we discussed earlier. What we did was, after resampling this to multiple sampling frequencies in the test set, we resampled them back to these sampling frequencies because that is what the model can take as input. And we are doing this to test the robustness of these models against resampling. So what happens when you just resample the data? So these are the main results. Now here, these are the neural operator based baselines. So now again, neural operators learn function to function mapping. So in order to test these on classification problems, what we did was we replaced these convolutional layers with those neural operators. So those neural operators learn function to function mapping. The input and output is exactly the same. And then we added the rest of our framework to convert those neural operators into classification models. Other than neural operators, we compared our model against state-of-the-art task-specific baselines such as use sleep and attention sleep, which are sleep staging state-of-the-art models. And we also compared against Labram, which is a large pre-trained model, which is pre-trained on thousands of hours of EEG data, and also some strong baselines, including ResNet, Patch TST, and EEGNet. Now, in the results, you can see that our model outperforms all the neural operator based baselines. This basically shows the effectiveness of using spline based convolution, which is really good at extracting features from these physiological time series. And it almost matches the frequency of the accuracy of the state of the art model. So for sleep staging, the state of the art is sleep, and as you can see, our accuracy is very close to the accuracy of sleep for both the sleep staging datasets as well as sleep EDF. Now these plots show the robustness to sampling rate shifts. So as I explained earlier, this is for the ISRUC dataset where the sampling rate was 200 hertz. So we trained all the models at 200 hertz, and in the test set, we resampled the data ranging from 80 hertz to 1024 hertz. Now, as you can see, this light blue model is our NeuroCNN model. So this is pretty consistent and flat across sampling frequencies. If you look at other neural operator based models, which are these two and this last one, these are also pretty consistent across all the sampling frequencies, but our model achieves a much higher accuracy compared to these. But if you look at all the other conventional baselines, as you go below 200 hertz, the accuracy of these baselines start dropping. Now, this is just because we resampled the data from 200 to 80 hertz and then back from 80 to 200 hertz. Just this resampling reduces the accuracy. This is also a similar plot for the HMC dataset, where the training sampling frequency is 256 hertz. Now, the third plot shows the worst case accuracy drop across 5 folds for these two datasets. What this means is in the testing dataset, this is the difference in accuracy between the training sampling frequency and the sampling frequency where the accuracy was lowest. So as you can see, our model has almost zero accuracy drop, worst case accuracy drop, and so does Fourier neural operator, which is another neural operator baseline. But all the other conventional baselines have a much higher accuracy drop because of change in because of resampling. So this basically shows the effectiveness of using a neural operator style approach where you're treating the signal as a continuous time signal instead of a set of sample, and you're not resampling the signal. We also tested our model against various types of noises that are commonly present in physiological signals, which include power line noise, baseline drift, EMG, and Gaussian noise. So here the blue line represents our model. The orange is the Labram, which is the pre-trained model, and USleep is the task specific baseline. And these numbers basically show the accuracy drop when you add noise in the test set. So that in this case, the training set was all clean data, and in the test set we added all these noises. So as you can see, for power line noise, the accuracy drop of NeuroCNN is almost zero. Similarly, for EMG, the accuracy drop is zero, whereas if you look at Labram and USleep, the accuracy drop is 30 to 40%. For baseline drift and Gaussian noise, we have minimal accuracy drop. But again, if you compare it to the other two baselines, the accuracy drop is a lot. So this shows that our model is very robust to noise as well. Now, this is one more comparison. So in the convolutional layers, we used spline to parameterize our continuous kernels as functions. Now, instead of spline, you can also use an MLP to parameterize kernels as continuous functions, which was done by a paper titled CKCon, where they introduced continuous convolution, in which they implemented the kernels as continuous functions using an MLP. So this plot basically shows a comparison of spline versus CKCon. And you can see that spline is again pretty flat across all the sampling frequencies and achieves a much higher accuracy compared to all the variations of CKCon. So in CKCon, there is this hyperparameter, which is the hidden dimension of the MLP, which is used to generate the kernel. Now, as you can see, as this hidden dimension increases, the sampling rate robustness decreases by a lot. So 100 is the training sampling frequency, and at 100 hertz in the test set, we achieve the highest accuracy. And as soon as you go either below or above 100 hertz, the accuracy drops significantly. Now, why is this happening? Let's try to understand why spline is better in this case compared to MLP for sampling rate robustness. Okay, so the key idea is that spline parameterization gives explicit control over the kernel bandwidth through control point density and physical duration. So as I explained earlier, in spline we have two hyperparameters. One is the number of control points, and the other is the physical duration of the kernel. Now, by choosing these two hyperparameters, you can effectively constrain the total bandwidth of the kernel, which means that you can constrain the maximum frequency that this kernel can have, which is approximately given as, this should be, where NC is the number of control points and L is this length of the kernel. So if you increase the number of control points, if let's say I add a few more control points here. Then your kernel can basically have higher frequency component. If you add a lot more control points, then it can have even higher frequency components. And also, if you keep the control points fixed and reduce this duration, then also the maximum frequency in the kernel will increase. So using these two parameters, you can control the maximum frequency that can be present in the kernel. Now, why is this important? So as we discussed earlier, this kernel is a continuous function, and we have to sample this kernel based on the input sampling rate. Now, whenever we sample a continuous signal, we have to make sure that the Nyquist limit, we have to make sure that the sampling frequency satisfies the Nyquist theorem. What is the Nyquist theorem? The sampling frequency has to be at most, I'll put it in another way, the maximum frequency in the signal has to be at least twice the sampling frequency. So if so, f max has to be greater than or equal to 2 times fs. If f max is less than 2 times fs, then aliasing occurs. So, for example, if this is your kernel and your sampling rate is high, then you will capture this exact same shape. But let's say if you sample this same underlying signal at a lower sampling rate, and then your signal shape will completely change. That is what's called aliasing. Now, in the case of spline, because we can control the f max, we can choose the number of control points and kernel duration. So the kernel respects the Nyquist limit of the lowest input sampling rate that the model can have. So for example, if you're dealing with EEG data, you generally keep frequencies up to say 35 to 40 hertz. So you can safely assume that the lowest sampling frequency that your model is ever going to deal with is 80 hertz. And based on that, you can set your number of control points and the duration of the kernel so that your kernel always respects the Nyquist limit of. Now, in the case of an MLP, we don't have any control over the bandwidth of the kernel. When you're using an MLP to parameterize a kernel, this kernel can take any arbitrary shape and can have any frequency components. And because of that, if you train your kernel at say 200 hertz and your kernel looks like this, and if you sample it at 80 hertz, then the kernel shape can completely change, which is why the accuracy of the model reduces. That's why we see these huge drops in the accuracy, because as we increase the number of hidden channels, we are giving more degree of freedom to the MLP to generate the kernel, and the kernel can generate more arbitrary signals. And that's why when we sample those signals at other sampling frequencies, basically the underlying kernel changes completely due to aliasing. So that's why spline is a much better choice, because it gives you inherent regularization over the bandwidth of the kernel. So in conclusion, the NeuroCNN model learns a function to label mapping for physiological time series classification. The model achieves strong performance across EEG, EOG, and ECG datasets maintains stable accuracy under unseen sampling rate shifts, and shows improved robustness to test time noise. And beyond physiological signals, this can be used for any other continuous non-stationary time series signals where the same underlying process may be recorded in at different sampling rates. So any if you are recording any signal using any sensor where you are using an analog to digital converge A to D converter where you are sampling the signal, this model will be useful and it will increase the robustness across sampling frequencies. So that's it for this presentation from my side. Thank you so much. Let me know if you guys have any questions.
Awesome presentation. Awesome. Nice.
Thank you. Thank you.
Anybody has any question?
Great presentation. Can
Thank
you
you.
please go to your slide number 9?
Slide number 9.
Yeah, you showed us this formula maximum sinusoid frequency, right? So is it something you formulated or is it an existing formula in the literature?
Okay, so this formula comes because the sinusoid frequencies are
Mm-hmm.
omega k t and omega k is 2 pi k by t.
Mm-hmm.
So as you increase this k, one,
Mm-hmm.
2, 3, 4, 5, 6, the
Yeah.
frequency, these frequencies are basically not random. They are
Mm-hmm.
calculated using this formula, right?
Mm-hmm. Yeah.
So as the k increases, this omega k increases, the frequency of these sinusoids increase.
Mm-hmm. Okay.
Now, this k basically goes till m.
Okay.
Now, so
It's
yeah,
not
so
visible if you're writing.
no, okay. So this k basically goes till m,
Mm-hmm.
and m is the total number of sinusoids that you're using.
Mm-hmm.
Okay.
Yeah.
So f max is approximately equal to m minus 1 by 2t.
Okay. So it's coming from the frequency
It's
formula.
coming from the way we are choosing these frequencies.
Okay. Okay. Nice. Yeah. Got it. Thank you.
No
And
problem.
one more here. Can you go to the main architecture diagram? Mm.
Okay, so one more thing. This m
Mm-hmm.
minus 1 by 2 is because so the first basis is basically the DC one, which is
Mm.
1. So we are
Okay.
subtracting that from
Initial.
the total number of frequencies.
Okay.
And by 2 is because we are using the same frequency for both sine and cos. Okay.
Yeah. Okay.
So that's m minus 1 by 2.
Mm-hmm.
And frequency is basically 1 by time period.
T.
So
Yeah. 1 by
yeah,
T. Yeah. Okay.
yeah, yeah. So what were you saying?
Can you go to the main architectural diagram?
I mean, it
Yeah.
is.
So Uh, while we are converting, as I can see, like this Fourier basis pooling, we are only changing n to m, right?
Yeah.
And how we are getting this n, like from this line convolution 1D?
So n is basically your
Yeah.
input length
Okay.
in samples. So let's say you have an EEG signal
Mm-hmm.
of length 30 second and you sample
Okay.
it at 100 hertz.
Mm-hmm.
So this will give you 3000 samples, right?
Mm. Yeah.
So n is basically 3000.
Okay. That's
Now
the number
when
of
you,
samples. Okay.
yes, that is the number of samples. And when you use convolution with the same padding, you must have used CNNs with same padding.
Mm-hmm.
With same padding, the input and output lengths are the same because you add zero padding on both sides, right?
Mm-hmm.
That is exactly what's happening. So that's why the input and output lengths are the same. So if the input is BCN, the output is also BCN.
Okay. Okay. Got it. Yeah.
Yeah,
Thank you.
no problem.
I have a question.
Yeah,
Uh, and first of all, this is great work, and the results are pretty strong. And congratulations on the paper.
thank you.
Uh,
Thank you so much.
One question I have is that,
Yeah.
here in the architecture, you are passing the
Mhm.
signal uh, BCN into spline
Mhm.
convolution and getting another BCN, and then
Yeah.
passing it through Fourier basis pooling. I was wondering,
Yeah.
why can't we just give the signal to the Fourier spectrum, like the splitting this, and then just directly putting it through transformer instead of going through the spline pooling? Like, what value does the
You can.
spline?
Y- Yeah, yeah, yeah. So you can definitely do that. So you can use the Fourier basis pooling first, and then use anything like transformer or anything. The reason we are using spline convolution is that we first want to extract the meaningful features from the data. If you use Fourier basis pooling before extracting these features, you will out of the box lose all the temporal information. So the formula for Fourier basis pooling is integration 0 to m, and then you are basically multiplying this basis with the signal. So this integration part basically gives you only one coefficient per sinusoid. So you lose all the temporal information. So
Mhm.
these convolutional layers basically first filter the signal, reduce the redundant information, and extract the meaningful features. For example, in EEG, there are specific patterns associated with specific sleep stages. So it
Oh,
is basically filtering those, extracting
okay.
meaningful features, and then we are using the pooling. So the pooling, sees these meaningful features and
Okay.
frequency components which are enhanced
Mhm.
by these convolutional layers.
So the
that is
spline
why
convolution. Sorry, go ahead. Sorry.
that is why when you see this comparison between NeuroCNN and all the other neural operator based models, the limitation of all the other neural operator based approaches is that they are not as good as convolution in extracting these features. So, for
Mhm.
example, Fourier neural operator does not look at localized features in these signals. It looks at the broader frequency spectrum of the signal. And localized patterns are very important in these signals. So that's which our CNN extracts really well. So that's why our accuracy is much higher compared to all these models.
Mhm.
Yeah, and also like these neural operator models are performing worse than just a small EEG net model, right?
Yeah, yeah,
Mhm.
yeah.
Mhm.
The reason is
Yeah.
again the same. But
Mhm.
again, they are really consistent across all the test and sampling frequencies. But their accuracy is not so good because they
Mhm.
are not able to extract those features.
Okay. Okay. Just one follow-up question.
Yeah.
The spline convolution kernel. So you're not training the kernels. You have those kernels available. You are running it through the.
So, okay, that's a good question. So, in these kernels, we are basically training the positions of these control points. So, after, let's say, after a few epochs, this kernel can maybe look like, you know, this.
Mhm.
So it will become like this. So we are basically training this the position with respect to the y-axis of these points.
Mhm.
The position with respect to x-axis is fixed, and the number of control points is fixed, but the kernel shape can change based on their position on the y-axis.
Yeah. Okay. Yeah. Thank you. Thank you. And once again, the parameter that table, it just shows how much efficient your model is compared, like the other models are having like millions of parameters, and you're matching or beating them with
Yeah.
like less number. So great job, and thank you for the presentation. Thanks.
Thank you. Thank you so much.
Anybody else has any question? Okay, so I think that I will stop the recording here.